welcome back to Family Physics. In this video, we are going to do some more examples on the Broglie wavelength. In this example, I am going to do an electron that will be accelerated from rest through potential difference, and using that to find the kinetic energy, momentum, the Bruy wavelength, and eventually showing this relationship down there. Okay, so let's begin. Starting with question A, we want to find the kinetic energy of this particle. We know that the kinetic energy of this electron is going to depend on the potential difference that it has been accelerated. And if it's accelerated from rest, then whatever that potential energy that it it loses from going through the potential difference will be converted directly into kinetic energy. So that the work that this potential difference does is equal to the potential difference times the charge of an electron. And this work that is being done is going to get converted into the kinetic energy of this electron. So if we take V and we times it by Q, which is 3.0 times 10 to the power of negative 2 volts, times the charge of an elementary particle, 1.6 times 10 to the power of negative 19 coulombs, then we will get 4.8 times 10 to the power of negative 21 joules. So here's a little side interesting thing, is that oftentimes in your questions you might see an electron having a kinetic energy of something EVs, so electron volts. So in fact, if we wanted to convert this into electron volts, we need to divide by 1.6 times 10 to the power of negative 19 electron volts. And if we did that, we would get exactly 3 times 10 to the power of negative 2, which is the amount of electron volts. So this amount of work here, the amount of kinetic energy that this electron is going to have is essentially 3.0 times 10 to the power of negative 2 electron volts. Haha, which is exactly the potential difference in this question. So we can kind of see where the electron volt may have came from in terms of convenience. Okay, so next up we have B, the momentum of the electron. So we know that the momentum of the electron is going to depend on its kinetic energy. And since we are not talking about very high voltages, so this electron is not going to be able to go so fast near the speed of light. So to look at the next couple of questions, we only need to look at the classical model. So that's so for momentum, since we have the kinetic energy there, we know that in our data booklet, we know this relationship in which the kinetic energy is equal to the momentum squared over 2m. So classical theory there. So if we want to solve for the momentum, rearranging this, I am going to get momentum is equal to 2 times the kinetic energy, the mass, and taking the entire square root. So this is going to give me 2 times its kinetic energy in the previous question in joules, 4.8 times 10 to the power of negative 21 joules. The mass of the electron, which is 9.11 times 10 to the power of negative 31 kilograms. And that's going to give us, I get 9.35 ... times 10 to the power of negative 26 kilogram times meter per seconds. Okay, so if we round it off, this is 9.4 times 10 to the power negative 26 kilogram meters per seconds. Okay, so that would be finding the momentum. So not too bad so far. Last but not least, find the Bruy wavelength of the electron, in which now we have the momentum. We can just go ahead and calculate this out. So using the non-rounded value from the previous question, we get 7.089 ... times 10 to the power negative 9 meters. And here we go, rounding this to 2 sig figs. So here we go. This is not very complicated, although given this question, notice that A, B, and C kind of led you to the Bruy wavelength. But this could appear as a single question in which you need to know all the steps in between to get you to the final de Broglie wavelength, okay? So that's kind of what number 4 is going to do, is to show the relationship between the Bruy wavelength and the electric potential the electron accelerated through. We want to show that it is equal to, equivalent to this. So since this is so much related to the previous question and that did not take so long, let's do this as well. We know for finding the de Broglie wavelength, this is lambda equals to h over the momentum. Okay, so what looks different here is the square root of 2 MeVs. Okay, so that's the part where we have to show that that is essentially the momentum of this particle. We know that the kinetic energy of a particle is related to the momentum in this following relationship. So to show that the momentum show momentum as a function of the kinetic energy, this is just P is equal to 2 EK times the mass and all that taking the square root as shown previously. As for the kinetic energy, we saw that the kinetic energy of the electron that was accelerated is essentially the work done by whatever electric field is produced by the electric potential, and this work done is equivalent to the kinetic energy equal to the potential difference times the charge of an electron. And you know what? It wants this question wants E for the charge of electron, so VE instead. So then we can plug this in back here for the kinetic energy. So we have momentum is equal to the square root of 2 times VE times M. Vem, like venom. Venom, spelled differently. So this momentum, ultimately, we can then substitute it back into the de Broglie wavelength. So we have the wavelength here is equal to the Planck's constant divided by the square root of, okay, let's put all this in order, 2, M came second, then E, and then V. Okay, so there we go. All right. So that's it. This is kind of the idea for using the Bruy wavelength and on an electron that's been accelerated. Okay? So, hopefully you learned something from this video and you found some answers to your questions. I wish you the best of luck. Thanks for watching Fat Mama Physics, signing up.